And the next presentation, equally important and very interesting. It is Knots, Physics, Mathematics, and Sustainability, Louis Kauffman. So this we'll see in the perspective of mathematics. Now, this is a little bit challenge when I suggested this. So how mathematics is linked to sustainability. So, sure, please. They're coming. So, mathematics and sustainability. So, mathematics is, totally fundamental science. And sustainability needs application. So, application could be in 100 years, that's fine with that. But in order to see the effects, is to shorten the distance between the fundamental and application. And this is one of the reasons of SIPS. So we start from all fundamentals with the goal how to apply them as fast as possible. Some of them, sure, you cannot. But that's the goal, and we try to do that. It's important to have fundamental science because everything starts from fundamentals. And the application cannot be without fundamental, there will be no applications. But if we shorten the distance, if we, tackle the application while we think about fundamentals, it's another concept. When you develop a new theory, it's better to think also how this will be applied. By the way, you got the microphone. I remember I was invited for a plenary lecture in Mexico, and one of the Russian mathematicians, he took a paper, a sheet of paper, he did it like this, opened it and said, my lecture will be to model this. It was just a chunk of paper.
Folding. Ways of folding the paper?
Folding a paper irregularly, and says, my lecture will to model this. And it was an excellent lecture. But I asked a question, how can we apply this? He said, there is no application. So, this is good, but we try to apply, so please.
Okay, you can hear me? Right, the question that we're going to try to talk about is the relationship between mathematics and sustainability. And I think part of the problem of that is that we're so close to it. We're using mathematics all the time. Our world is built out of mathematics. It's worth thinking about that, about how influential Newton's discoveries were, and the electromagnetism, and how the whole world is just wired up with mathematics in that way. And yet, on the other hand, we're often not thinking directly about mathematics, or we're thinking, well, that's something that people are writing or solving equations, something like that. So I want to find some choice where we could look at very fundamental mathematics being how mathematics is being created, or how it goes all the way to our thought and our language. And on the other hand, to see how it's related to certain applications. So I chose to talk about what I call biologic, which is mathematics, topology, biology, sustainability theme. And on the other hand, I wanted to begin this not with the slideshow, but with the little MP4 that you'll find in the same box. If you could run that.
The great physicist Paul Adrien Dirac devised a topological trick with strings in order to illustrate graphically an elusive property of the spin of the electron. In quantum mechanics, all particles are connected to each other and to every observer in the universe. For an electron, there is a quantum state or wave function relative to a given observer. If this observer should walk around the electron, making a full turn of 360 degrees, then the wave function changes sign. This means that while a quantum mechanical system involving electrons is not brought back into exact coincidence with itself after it is rotated by 360 degrees, it is brought back into coincidence with itself after it is rotated by 720 degrees. Here is Dirac's visual metaphor performed as the Philippine wine dance. Watch closely how the dancer winds the cup through 360 degrees, acquiring a twist in her arm. Then she winds the cup through another 360 degrees, and the twist in her arm has disappeared. Notice how the ribbon is moving around the inner sphere. The ends of the ribbon do not move. They are fixed to the respective spheres, and yet now the ribbon returns to its original position and all the twist is gone. This is the Dirac string trick in modern form. We have programmed the computer to twist the space between the spheres. The strings, whether one or many, are located in that space and acquire their twist from the twist of the space. Once we untwist the space, the strings untwist as well, and we have given you a glimpse of quantum mechanical reality.
We made that little film a long time ago. One of the reasons I wanted to show it is because I can now say that I showed our film of the Philippine wine dance in the Philippines. But the film is illustrating how close you are to some very interesting mathematics that you might not have thought about, because it's showing you that you can interpret the square root of -1, not by a 90-degree rotation, as you might have learned in school, but by a 180-degree rotation, which is the twist of the belt, 1/4 turn, 1/2 turn, 1/2 turn of a belt. If you turn it 1 full turn, you get a 360-degree twist on the belt, but that won't go away. But if you allow yourself to go through 720 degrees of turn, you can come back exactly to where you started. And this is seen on a belt, just like the film illustrated, so that this mathematics, now mind you, right, that was a square root of -1, that is something of order 4, right? You turn by 180 degrees, and if you do that 4 times, you'll be back where you started, because a 180-degree turn done 4 times takes you all the way back to where you started. And we could illustrate it once again with my rope here if we want to. There is no twist on the rope. I'm going to try it this way. Let's see. Up, then. And I'm going to twist this by 1/2 turn, 2 half turns, 3 half turns, 4 half turns, and now there's 720 degrees of twist on the belt. Now, what I want to think of is, I may be in trouble here. It would have been better if someone else was holding it. But let's have my other arm holding it, and there's 720 degrees of, a helper. Very good. So you'll hold on to that, and we'll start again. There. All right, so we're going to put 1, 2, 3, 4. So this has 720 degrees of twist in it. And now you should think of this as a ball in space, like in the film. But in order for this to go around the ball, I'm going to exchange hands. But it's not meant to be a sleight of hand. It's just that it gets to this side of the ball, and now I replace. Now it's on the other side of the ball. We come back, and there's no twist on the belt. Thank you. But now that means that you can do it in any direction in space. So I want to go one step further as long as we're playing with this. You can do this in any direction in space. So you can turn your arm this way for the arm pointing out. Let's call that I. And you can go by 180 degrees around the vertical and call that J. And you can go by 180 degrees around this horizontal going that way across my body and call that K. And now I have 360 degrees on the belt, on my arm. So this is the -1. This is 360 degrees. So what I found was that I, J, and K, that screw motion, creates a 360 degree twist, but 360 degrees is -1. So I and J and K together give us -1. And you have operations along I, along J, along K, and each one is a square root of -1. And what you are looking at is the quaternions, the famous non-commutative algebra invented by Hamilton in 1843, but it's on your body. You carry it on your body at all times. And it's parts of that are happening in that dance, and it's with you all the time. It's with you in the way you orient to the rest of the space. So I wanted you to think about that, and you could try it. So maybe you would like to try it before we leave this part. If you would hold your hand out like this, right hand, and turn by 180 degrees, that's I, and then turn your hand 180 degrees so it's pointing at your body, and that's J, and then swim underneath like that and find that you now have your arm pointing out in a somewhat painful configuration that is 360 degree twisted, and that's I, J, and K giving you -1. So that's the quaternions on your arm. And the film showed that it was related to physics, and it claimed that you were getting a glimpse of quantum mechanical reality. And again, this is showing you something about mathematics and metaphor. We probably shouldn't leave it, but remark on it, because it is the case that if you had an electron and you walked all the way around the electron once, the phase of the wave function would change sign. If you go around twice, the phase of the wave function will be back where it was. A full 360 degree rotation does not return you physically to where you are. But you don't have belts attaching you to the electron, or if they are, they'd be invisible. But this visualization, which was originally due to Dirac, was a way for him to explain that in a palpable way. And some people would like to perhaps imagine that there are invisible strings attached to the fermions, but when you actually try to do the physics the way we normally do it, we don't try to attach invisible strings to things. We have to think about symmetries in a different way, and the mathematics gets more abstract than the palpable things that are going on directly in space. So this is part and parcel of some of the things that go on mathematically. But this isn't addressing yet the notion of sustainability, except for the sustainability of mathematics in relation to the sustainability of space itself. Because part of the fact that we have a stable three-dimensional space is related to the fact that we relate to it mathematically. That's the thing that I think I'm showing you, in my opinion, I'm showing you when I show you how a deep mathematical structure is directly related to the way your body orients in space. I'm showing you that the sustainability of your perception and being in space is related to mathematics. But let's try again using the slideshow. So, excuse me, I'm going in the wrong direction here somehow. One more. Okay, so there we are. That's the beginning. And then, as I said, we're concerned with how mathematics is related with sustainability. since mathematics is ubiquitous and related to all modeling and descriptions of our worlds, it will help to think about this via biology, topology, and specific yet elementary situations. And of course, we could have done physics, but I chose things that are related to biology, and you'll see, I think that this is a good choice. So this is our situation of being in the world, that we aren't separate from the world, and we are, in effect, representatives of the world observing itself. And then this is that one was an artwork by some unknown artist, and this is a little artwork by your lecturer. And it's showing a mathematical fantasy of self-reproduction. But we might look at this because things are happening apparently continuously in my picture. But they couldn't be completely continuous because a continuous little protoplasmic entity like the guy on the top has to divide into two, so some kind of discontinuity has to happen. And you might be interested to look at it carefully to see where the discontinuity was. And you'll see it's a little sleight of hand down there near the middle as the snakiness slides back and forth in some funny way and reconnects, and then the little circle comes out. So it's very similar to the kind of thing that you might ask when you're looking at the rope. What sustains a knot? Everybody is aware, now we're talking about mathematical sustainability. What sustains this knot? What keeps it there? It won't go away. You have enough experience with knots to know that the only way I can get this knot to go away is to slip it off the end of the rope. Otherwise, it won't go away, right? So the magician comes up to you and he says, but this is very special magic rope, and I tie the knot in this magic rope, and it does go away. So what happened? Well, I lost sustainability that time. And how did I lose sustainability? Of course, the magician isn't supposed to explain to you how it happened. But in this case, for the sake of our discussion, I should explain to you how it happened. How did we make the knot sustainable? We made a loop, and then we put the rope back through the loop. But if you put the rope back through the loop one way, it's sustainable. The knot is held by the way you put the rope back through the loop. If you put the loop back through the other way, the exact other way, this way, well then it does not hold the loop and it falls apart. The magician will make the loop and then apparently make the knot and pull it up tight, but he's concealing the fact how he put it through, and so it's easy for the knot to disappear. So that's one issue of sustainability. The other one that is the mathematical question that is always in front of us about knots. Now I have too much rope. I wanted to just use the blue side. So I make a knot in the rope, and this is an honest knot. And then I make another knot in the rope. Hopefully, yes. Okay, so now I have a square knot, if you can see it, and it's nice and stable, and it won't go away. And then I weave down through the bottom of this, and I assure you this is still knotted. And then I do another weaving, which doesn't look too much different from everything I've done so far. And I have this thing in front of me, and now there's no sleight of hand that's going on. And if you're looking at it, if you could see it, or if we were close and you could look at it, you would see that inside of this, there's definitely knotting going on. But if I pull on this, it all goes away. It's not sustainable. So then you have a mathematician's problem about sustainability. Under what circumstances is such a thing like that going to be knotted, and under what circumstances is it not knotted? So that becomes a really interesting mathematical problem that people are still studying to understand how to take the combinatorial apparent geometric structure that's right in front of you and find out how to calculate from it to determine whether or not it's knotted or not. And there are many different strategies for that. So that's where that goes. And then one more thing about knots is pattern integrity, which is also a general theme. So what I'm hoping is that by my telling you about some of my favorite particular mathematical themes, you see also that these themes are very general and would apply to many other systems other than the topology, but the topology illustrates them very well. Here I have a knot, and it is on the blue rope. But the knot is a pattern, and it's a movable pattern because we're talking about topology, and this pattern can be transported until it's on the red rope. And by the time it is on the red rope, by the time it has moved all the way over to the red rope, every molecule is different, right? It's the same. One would say it's the same knot, but it's sustained by an entirely different substrate. And the metaphor is easily illustrated with knots, but goes all the way over to biology as well, because it's the same thing. You as an organism are a certain kind of pattern that is going forward in time on the substrate that you are, but that substrate is changing all the time, its components, but the structure goes on. And so the theme of sustainability with regard to mathematics and the theme of sustainability in biology are identical. Now, I'm not talking about the question of how do you manage to sustain it, but just what sustainability is, right? And then it becomes very interesting to think about what is it exactly that is going on that a pattern, an abstract pattern, a pattern that need not have any physical realization, nevertheless does have a physical realization and can live stably on certain kinds of material substrates. And how far does that go? Is the material that you're looking at also patterns on something, and do the somethings eventually disappear? Do they turn on themselves? What is happening? Another example of this same phenomenon is the following. I might create a knot on the rope by the usual magician's method, and now I have a knot on the rope. But I'm not going to use any more magician's methods. What I want to illustrate is that I could get the knot from the rope without using any magician's methods. So that means I'm going to allow myself to manipulate, but I won't let go. You would have to get somebody here to check that I'm not letting go, but maybe you can see that I'm not letting go. But where am I now? Well, there's no knot on the rope. So we're partway out into getting the knot somewhere else. But where is the knot right now? Maybe it's clear to you, maybe it isn't, but I can go further, and then everything becomes more or less clear. I can go further, and now there's absolutely no knot on the rope, no question about it. It's off my arms, it's just touching my hands. And now I can ask you where the knot is, and I think it's obvious to everybody where the knot is. It got transferred to my arms. So now my arms are knotted, and the knot is off the rope entirely. So the pattern got transferred to a completely different substrate, and then if we go backwards, we get this midway point where the knot is composed of rope and arms, and then the original point where the knot is on the rope. And that kind of transfer of pattern is going on all the time in all of these systems and is worth thinking about. How are we doing in terms of time? Excuse me, there's a watch in my pocket. All right, so maybe I should just skip to one aspect of the biology and stop, yes? So you're going to see me going through these slides without commenting on them to get over to a certain point. Because I wanted to talk about, well, I can't resist that one. Let's hold that one for a moment. This has to do with how do things appear and how much of what you see is a pattern that you've imposed on your own inputs. Because here we have a nicely sustained Necker cube. Then it's an optical illusion. It's a cube, and it's also a cube that can be seen in two different ways, and everyone sees it. But if you look at what you're actually seeing, or what the input is to the system, it's some circles with funny little patterns on them, and all the rest is your construction. Another example is this. Here is an object which has the appearance of being an object, but it isn't an object in three-dimensional space. It's an imaginary object, but your way of constructing sustainable world makes this a sustainable object for you. But when you occlude part of it, you immediately process it a different way and see that it is a realistic picture of some logs which are not touching underneath the black circle, if you occlude it that way. But if you occlude it this way, then it is not touching underneath that black circle. And if you do this, it's not touching under that one. And when I hit the button one more time, it's going to go from what is apparently realistic to imaginary in some micro time for your observation. And all those have to do with your sustainable observations. I don't know how to make mathematics out of that, but that kind of thing is also going on all the time. I'm skipping everything else, but wanted to talk about DNA replication, and which of course is fundamental for biological sustainability. But what does it look like? Sorry, we're going to go back. I didn't time this as well as I wanted. Oh, all right. Reminding you how DNA replication works. The DNA is two strands interwound with one another. Enzymes pull the DNA apart, and the environment provides the complementary base pairs to the broken base pairs, and you end up with two DNAs. And there are many problems about how they would then get apart. That's how DNA reproduces. The thing that is of interest here is to think about what kind of reproduction is that. And if you think about it, you realize, well, what you have is a strand which, if left to its own devices, will build its own complementary strand in the environment. And that's how it works. So that you have this, so the reproduction is happening by a certain entity is incomplete, but within its environment, it gets completed and complemented, and the reproduction occurs because of that. And that is probably more fundamental than the ways that we think of talking about reproduction from a computer science attitude. And it's more general, if you think of it that way, than what happens in the biology. Very general, that things work together with their complements. So things work together with their complements. And I'm skipping everything, except to show you one topological example, and then we'll stop. here is a topological entity which is fixed at the top and fixed at the bottom, just some strings going down. But if you pull it apart a little bit, then the topological environment can provide the complementary parts. The little blip at the bottom, there it is, and the little blip at the top. But you see, they pair together and come right out of the environment, topological environment, not biological. And then we cut it, and you have two of them. So, so you see that same theme of how the environment could provide the complementary parts could happen in a topological situation just as well as it could happen in a biological situation. The analogy is interesting to play with. And by playing with those analogies, one can think about how does one get to this fundamental replication of not only the object, but the information that is in the object, so that it can generate itself. It's back, the question in back of that, of course, is one that I don't know the answer to, namely, how did DNA evolve, right? But what I'm playing with here is mathematical analogs to self-reproduction that open that question up in different directions. And that's a question about sustainability at base. So we'll stop there.
So this is so interesting. My question is, can we describe mathematically any situation in the world?
Say that again, can we?
Can we describe, oh, sorry, it's my fault. I was removing this. Can we describe mathematically anything that happens in the world? Any phenomena, can we describe mathematically with an equation?
Can you describe anything mathematically? You can try. But in the trying, the language that you build may be getting in your way, or you may be creating something new. Like we live in the world where we count, right? We've been counting since we were children. So we look at a world of many objects and we count how many there are, and it's very useful. But imagine that you couldn't count, then would the world you describe be the same? I think it would be a different world if you couldn't count. You invented counting and you end up in a different world.
Okay, because mathematics is prediction, kind of. But the world is unpredictable. Can we put unpredictability into mathematical equations?
Predict, did you say?
Predicted. If you have an equation,
right. Well,
you predict in a certain way.
We all know that that's a tricky business, right? Think of Newton's laws, right? And we, in principle, can predict how somebody will orbit somebody else. But if you have more than two bodies and you want to predict correctly how the three are going to behave together, then it becomes very hard, and you end up really needing to model it rather than to try to figure it out analytically. And so if you're going to ask about prediction, you probably have to ask about modeling, like
correct.
Computer modeling.
But it's a mathematics on the background, correct?
Yeah.
So computer modeling is based on mathematics, correct? Mathematical logic, and we need equations.
Yes.
So, as I mentioned,
but there are many cases where there's going to be a shorter way than a way to analyze something into a set of equations and so on, and that's good, right? But that may not be at all the most efficient way to do it. There may be some much more direct way to understand it.
So as I mentioned...
But you can always try to model something.
Yeah, sure. I mentioned is the Russian mathematician in Mexico, where we were both invited to a plenary lecture. He took a piece of paper like this. He did...
crumpled it.
And he said, I'm going to model this.
Uh-huh.
Can you model this?
Right.
mathematics.
And then what would your next step be if you were going to do that?
So,
Well, I think your next step would be to slow it down, right? You would say, well, how can I fold this paper? I could fold it like that. That's the simplest sort of fold that could happen.
yeah, but that's
then-
not the case. He did it irregularly like this.
But then the very next one is already interesting. Suppose we fold it over there like a little S curve, and that comes back down
That's
into a
predictable.
singularity right there. See,
That's predictable.
and you get a fold with a singularity
Correct,
like that.
I agree with that.
And
That's
then you realize, oh, this is going to be more complicated than I thought,
Yeah.
and you start playing with this. Oh, we knew an artist named Ron Resch. Maybe you've heard of him, and he, not a mathematician, an artist, and he started folding paper, and he spent his whole career on what came out of that.
Correct. But he did it completely irregularly.
Yeah.
I'm going to model this. So it's,
But there is a
so
there
it
is
could
some-
be
there
this
is
way,
some
it could be this way,
Yeah.
could be different. It's unpredictable, the way you fold it.
Well, there are lots of predictions that are going to be very hard.
No, I mean it's to model it. I'm not saying predictions. It's a little bit of long term, but how to model this, which has unpredictability. You can fold this way, you can fold this way, you can fold this way. So there is no. So next year
Well-
you're going to give a reply for this.
Oh yeah, we can think about it, but notice that what you really want to do is learn what the paper does,
Yeah, correct.
and then
Well,
after a while, some of it will become mathematics, and
Correct.
some of it will become practical knowledge,
correct.
and
So
you
that's the
have to
difference.
combine the two.
Yeah, that's practical knowledge and mathematics. So mathematics follows the practical knowledge or vice versa.
They follow each other.
They follow each other, correct? Yeah. So mathematics as it is right now, it's a little bit limited to the practice, correct? They follow each other, but they're not the same. So it's a little bit limited. Can we make it to that's why my question. Can we mathematically describe everything in this world? Which I guess the reply is no. Or yes.
Not right now.
Not right now. Good.
And also, you get as soon as you have mathematical things, as soon as you have a set of rules that you can follow, then you can almost always make up questions about the way those rules behave that you never were able to ask even before, and that goes on forever. Nearly unsolvable problems within the mathematics.
Yeah.
Problems
so-
about predicting how the mathematics itself will behave. Because as soon as you start creating language of some kind with rules, you you've opened Pandora's box.
Exactly. So the limit is the horizon. So much to be done.
Yes,
Can you think about this for the next year?
we will.
How to model this? Thank you very much. Really interesting. A pleasure to have with you. A pleasure to have you at the specific symposium on mathematics. And this is the last lecture of our plenary, day 3 of our summit plenary.